SwayamPrabha. Digital India. Educated India.
Hello, welcome to Basics of Noise and its Measurement. Today we will be introducing a couple of new terms which are very widely used in noise reduction industry and academia, and some of these terms are like transmission loss, mass attenuation, sound transmission class, noise reduction coefficient, and things like that. So I just wanted to introduce these terminologies because once you are done with this course and if you encounter these things in your workplace or in your college, you should have some idea as to what they mean. So the first thing is mass attenuation. So whenever I have some sound which is traveling across in a medium and I want to reduce the level of noise at the other end, then I can do it in 2-3 different ways. The first way is that I put a heavy piece of mass as an obstacle for this sound, and then less amount of sound gets transmitted across this block of mass. So this way of reducing noise level at the other end is known as mass attenuation, okay, where I rely on just mass and it's not rigidly fixed, it's actually free to move, but because it's mass and the sound pressure wave has to move this mass, so that consumes a lot of energy, so the other side experiences less sound level. So we will explain this a little bit more. So suppose I have sound which is traveling like this and I have mass here, okay, and this is some mass. This is my incident wave P plus, and because of this there is some transmitted wave PT. And what I am interested in is, so this is that PT should be very small compared to P plus. That's what I want. And here I am actually relying on this mass to do that. So without going into the mathematics of it, there is a relationship which connects PT to P plus, and that relationship is this. Complex amplitude of transmitted sound wave divided by P plus. So this is a complex number, is equal to 2Z0 over 2Z0 plus J M omega. Okay, what is Z0? This is characteristic impedance of air, so rho naught C. Then M is mass per unit area. Okay, so if I am putting a panel here and the panel weighs 100 kilograms and if the area of the panel is 5 square meters, then the value of M will be 100 over 5, which is 20 kilograms per square meter. So that is mass per unit area. And then omega is equal to 2 pi F. Okay. Or I can also express this in a different way, which is 1 plus J times M omega over 2Z0. This is another way. So what does this relation tell us? So what it says is, so we'll look at 2-3 possibilities. One is, what if omega if m omega over 2 z naught is extremely small compared to 1. Okay. What does that mean? That this term is extremely small compared to 1. Then in that case, Pt is approximately equal to P plus. Okay. So if m omega over 2z naught is extremely equal to small compared to 1, or I can also say m omega is extremely small compared to 1, or m times f times 2 pi is extremely small compared to 2z naught, or I can bring this thing to pi, or I can simplify this further. Then if this condition is true, then whatever I will be hearing on the transmitted side will be pretty much same in amplitude as to what it is being incident on this thing. So what does this mean further? Which means that if, okay, so what does that mean? That this will be true if either m is very small or f is very small, or both of them are very small. And when I am talking small in this sense, z naught over pi. Okay. So what this means is that if I have a low frequency sound, then I have to really put a very heavy mass to stop it from getting transmitted to the other side. Okay. Because it's the multiple of m and f which matters. Or if I have a very small mass, then most of the frequencies will easily pass through it, unless frequencies are extremely high. Okay. So if I have to make this mass attenuation effective, I have to keep on, and if I want to be, so at moderate frequencies and high frequencies, even moderate values of m can do the job. But for low frequencies, I have to make mass really large. And it's not specifically mass, it's mass per unit area. It's mass per unit area. And using this Pt plus over P plus relation, we can also calculate something known as TL, which is called transmission loss. And we can calculate it in decibels. And how do you do that? If you take the magnitude of this thing and square it, that will be the ratio of energy which is getting transmitted. Okay. So whatever is the ratio of energies which is not being transmitted, that is your TL. That is your TL. And then you can calculate it in decibels. Okay. So that is your transmission loss. So this is one important way to attenuate sound as it is propagating in a medium. So if I am talking and I place a wall at the other end, then it's then it will be for less values of m, most of the low frequency sounds will still get transmitted. High frequency sounds will get attenuated to a larger extent. So this is one way to attenuate sound. Second way is, so in this approach, I did not assume that sound is getting actually absorbed by the mass. All what is happening is that this pressure wave is causing motion of this mass back and forth. When the pressure is high here, the mass moves on the other way, in the positive x direction. When it is low, then it gets sucked back. So the only thing which is happening is that this energy due to pressure is getting translated into kinetic energy of the system. But there is no dissipation happening in this system. Okay. So, but we can also have sound attenuation through dissipation. So this energy could enter into the material, and because of internal friction and viscosity or whatever, it can get converted into heat and it can get lost. Okay. So that is another, so absorptive way. So this is another mechanism through which energy can be absorbed. Okay. And if more of it gets absorbed, then less of it is getting transmitted to the other side. So these are the two mechanisms through which a lot of attenuation of sound is it happens. Okay. So then there is this term called STC, sound transmission class. Okay. And what is it? It is used to characterize partitions. So what could be a partition? A door is a partition, a wall is a partition, a window is a partition. You can even put a plank of wood between, say, the noise source and the other side. That is also a partition. So they are used to characterize partitions to indicate how good they are at attenuating sound. Okay. And what is HC? It is a number, single number. So I can have a partition, a wall, and I can say its STC rating is 25, and it means something. What it means, we'll talk about it later, but it means something. And there are some international standards used to determine the STC rating of any partition. And there are some, so there is one standard, ASTM E413, then there is another one, E90. So these are there. Okay. Roughly, if the STC number is n, then you can say that if the incident sound is 100 decibels, then the sound which is being heard on the other side will be 100 minus n. Roughly. It is not an exact mathematical relationship, but roughly. Okay. So that is what, in a broad sense, STC number means. And this is basically used by Americans, and you see this number a lot of times even on some of the Indian stuff which we see. So they say that, oh, the STC rating of this door is 80, which means roughly if you have 100 decibels outside, then it will be 20 decibels inside, roughly. So STC, another thing to look at it is that STC measures how much sound is blocked. Okay. It does not tell you how much sound is being absorbed. See, some sound may be getting reflected also. Okay. Some sound may be getting reflected, some sound may be getting absorbed, and only whatever is left is getting transmitted. So it tells you how much sound is getting blocked. It does not tell you how much sound is getting absorbed. It's a very fundamental thing, because there is another thing called NRC. So this tells you how much sound is getting absorbed. And I will show you some values of STC. So what do these STC numbers mean? So they mean that, okay, so if there is some door, let's say, and you say that its STC is 25, it means that if I am talking on one side of the door, the other person on the other side of the door can, maybe he will be able to clearly understand what is going on the other side. Okay, that is what is the meaning of STC 25. If you go to STC 35, then the same door, if there is loud speech on this side, then the person inside the room will be able to hear something. He'll say, okay, there's something, discussion is happening, but may not be able to necessarily figure out what is being discussed. Okay. If STC becomes 40, then you say, okay, not much is being heard. So whatever conversation is happening in this room, it remains private. Okay. So it says sound transmission class. I would have thought that the more this number, more sound gets transmitted, but it's actually the other way around. The more the number, the less sound is getting transmitted. Okay. STC of 60 plus, superior soundproofing, most sounds are inaudible. Inaudible. Okay. So and so on and so forth. So you can look at this and you can get a general flavor of, qualitative flavor of what is the meaning of different STC numbers. And you can buy, suppose you want to purchase a ready-made window for your room, and you can specify the manufacturer, especially if you are designing it from an acoustical standpoint, that I want that this window should have a STC rating of 40 or 60 or 70 or whatever. So that is how you specify. A lot of times people sell partitions, you know. There are in big offices, there are cubicles and there is a partition. They also have a STC rating and they tell you how much sound is getting blocked. How much sound is getting blocked. They don't tell you how much sound is getting absorbed. So this is from Wikipedia, and this is another list from Wikipedia. And you have a range of different types of materials. Not materials, but partitions. So I am not talking about material. So this is partition and different STC ratings, and in general, if you have a single pane glass window like the window there, then it has a very low STC rating, 27. Okay. And then if you have a double wall, then STC rating goes up significantly. In aircrafts, the windows are double walled because you don't want a lot of sound from outside to go in and inside to go out, and also you want to remain immune because the engines are running outside. They are very noisy. So they have very high STC ratings. They're designed in such a way that their STC ratings are extremely high. So this is what STC rating is all about. And the next term which I am going to mention is NRC. Okay. So this is noise reduction coefficient. So STC rating, it could be for a structure, it could be for a panel, it could be for a window, it could be for a door. It is not for a material. You understand? Material is different. A door could be made of 20 different materials. The outer lining could be steel, inner could be some wood, then inside could be glass wool. But a window could have glass, outside on it you may have some gaskets and things like that. So STC is for the whole system. This is NRC is for specific materials, and this is basically amount of noise absorbed by the material when sound strikes it. So when NRC is equal to 0, it is perfect reflection. When NRC is equal to 1, it is perfect absorption. Okay. And this NRC, it has is in this format. NRC is in this format. So the first number is 0, then you have a decimal place, then this X could be anywhere from 1 to 9 or actually 0 to 9, and then the Y is either 0 or 5. Okay. So you can have NRC of 0.00, NRC of 0.05, NRC of 0.1, NRC of 1.5, no 0.15, and so on and so forth. But you won't have NRC of 0.27. Okay. And how do you calculate NRC? So you take the material and find its absorption coefficient at different frequencies. So you measure it at 250, 500, 1000 and 2000 hertz. Okay, these are the standard frequencies. And then you find it alpha 1, alpha 2, alpha 3, alpha 4. For the same material, you may have 4 different values, and you somehow average them up and you come up with the final NRC rating. Okay? You come up with the final NRC rating for that. Oh, I'm sorry. So you start with 125 hertz. So this is how you compute NRC. So this is noise reduction coefficient. So what is noise reduction coefficient? It measures amount of absorption. This is different. This is different than STC, which is amount of sound which is getting blocked. This is only about absorption. Okay. So that is there. And then there is another term called SAA. It is sound absorption average. And it is pretty much similar to NRC, but the only difference is that here the frequencies which we use to calculate NRC or SAA is from 200 to 5000 hertz. This is becoming more prevalent because a lot of sounds which we hear in practical applications, they don't limit themselves to 1000 hertz. They go up to 5000 hertz easily. So this is becoming more prevalent. This is the limitation, that it stops at 1000 hertz. Okay, it stops at 1000 hertz. It may be okay for some general music or things like that, but not for regular sounds. This is more practical. Okay. So these are some of these important parameters about sound absorption and sound attenuation, and we will close this discussion today, and tomorrow we will discuss 2 topics. How do you measure absorption coefficient of a material, and then in that context we will introduce another tool for acousticians, and that is called a reverb chamber. So that's all I wanted to discuss today. Thank you very much, and we will meet tomorrow again.